Hello guys, how you doing? Today we are going to be starting the physics lectures, and the way they're going to go is first I'm going to get into theory, then I'm going to explain what the equations do. I'm not going to derive things you don't need to derive, like Mr. Prof, but I'll just be telling you what the equations do and how you use them. Then we're going to go into problems from easy to hard, and we'll cover everything basically you need to know about the unit. Right? So today we're going to start with charges and polarization, Coulombs law, electrons, protons, etc. It's a pretty simple unit and it's pretty short. So there's actually a couple of things we're going to start with, and there are two fundamentals. You have your electron and you have your proton, right? The differences between them is, well, let's see the similarities. They have one common thing, which is charge. Both have same charge. Okay? So they both have the same charge, and that charge is 1.602 times 10 to the negative 19 coulombs. It's measured in coulombs. Oops, if I can just write. That's where it's measured in. Alright? Now you can't have half an electron. If I give you something that is charged with electrons, then has this times however many electrons there are. That's the total charge. Alright? Now what's the difference between them is mass. Proton, a lot bigger than electron. You don't really need to know this, just in case he asks, I don't know. It's about 1A. That's how many times it's bigger than an electron. Okay? Now the actual things you need, and these I'm pretty sure will be given, is their mass. So the mass of a proton is 1.672 times 10 to the negative 27 kgs. And the mass of an electron is 9.10 times 10 to the negative 31 kg. Alright? Now that's the main things about them, but the question is, what do they actually do? And so besides charge and mass, there's not much to them. But the magic happens is when you bring two of them together. So what happens is when I draw here a proton and I draw here a electron, there's a force. It's just like if I push on you, that's a force. So, oops. And so what happens is the force here is attractive. If they're opposites, they attract, right? Actually, I'm not gonna write this down. You should know this. What happens? Right? And if opposites attract, if they're the same, they repel. Okay? This force, so you're actually right here. Force depends on two things, right? Distance and charge. Okay? So the distance between them and the charge each one has. Well, each one is the same charge like we said earlier. What if I have two of them? Right now the charge on this side is more than this side. So the force is going to change. Alright? So that's the basics. Now what happens when we take these things into materials? Right? So we have two materials. Insulator and conductor. Right? What's the difference in both? Okay. In an insulator, electrons can't move. They just can't. Right? They can't move. They just like you have electrons in there. They can't move around. In a conductor, electrons can move. Alright, so electrons can move. Okay. Another thing is you can change the charge for both. you can change. Okay, so you can change the charge for both. You can charge them up. All right. And so the example for this is if I have a ball, and there's no specific reason why it's red, but if I have a ball right here or a circle, and what it actually looks like is you have protons scattered. Let's assume this is an insulator. All right, so let's assume this is an insulator. Right. What it will actually look like, well, you'll have protons and you have little electrons around them, you know? That's what it will actually look like. Right. Now, your protons will always be scattered out evenly. They're not gonna scoosh together because obviously they're same charge. And so they want to repel. So now this exerts the force that way, and this exerts the force that way. Then this exerts the force this way, and this exerts the force that way. And so they're all spread out. Right. Now what happens is when I bring a rod, whether it's an insulator or conductor, it doesn't matter. I put a lot of charge on this rod. Let's say I actually brought a wire, like an electric wire. I plugged it into my wall. I brought it, has full charge, and I touched it. Let's say they touch. What happens is, remember how I said the charge, because it's all the same, they want to spread out, so the force is evened out. So what happens is the charge will move from here. Well, this is positive. Let's say I have negative charge. We'll move from here to here because let's say this is very condensed. It's very like, you know, there's no space. This, like, even if this was positive, let's say, right? Even though this is positive, what these guys think, they're like, you know what? If I move into here, even though there's positive, there's just less positive. Like I'll have more space, so they'll move here. Okay, and when it moves, this object is going to be overly positive. Okay, so it's just when you count it, there's more positives. Right. Now you can do the same thing with the conductor. Same idea, not much difference. Now the question is, when this charge moves, where does it move to? And where it actually moves is the outside. So if I have a bar like this, positively charged, or even if it's neutral actually. Let's say this is neutral. Which means it has no charge, no positive, like it has positives and negatives, but they're equal to each other, so no charge, no excess charge. Now when I touch it, let's say I brought this has like, you know, squished pluses all around. When I touch it, these will actually move on the outside. That's where charges are stored. Okay? And the reason being, like we said earlier, in an insulator, you can't really move. Electrons can't really move. And so when I take an insulator, right, and it's neutral, and I add, and let's say I tap it with a very negative rod, what happens is the electrons can't move inside, so they'll actually stay on the outside because they can't move in the insulator. Okay, now in a conductor, so this is an insulator. Now in a conductor, when I tap it with a negative, what will happen is it will just redistribute the charges around the insulator because they can move. They'll run around and see where they're all comfortable, where like the forces are evened all out, and that's how it is. All right. And so that's really the difference between inductors and insulators. Just remember, insulators, charge can move around. Conductors, they can. When you charge an insulator, the charge goes around since it can't move. But when you charge a conductor, everything just shifts around for it to go. Another thing is, in a conductor, the protons don't typically move. Now, the protons can move in a conductor, but they don't typically move because let's say you have it like this, and you have like some negatives. Remember how we said negatives are a lot lighter than protons? So what's gonna happen? The charge is gonna be like, you know what? I'm too big to move. How about we just rearrange the protons so it just evens out? So that's why typically the protons don't really move. All right. So now it comes into polarization. So when I take a rod that is positive and I bring it near another insulator. So these are two insulators. Insulator. And this is insulator as well. I can't spell insulator. Okay, if this was neutral, so let's say what neutral would look like, something like you have the positive and you have a couple negatives around it. Okay? You have positive, couple negatives around it. Right, and so on. We'll just add one more. Alright, now when I bring this nearby, what actually happens is the electrons, Jesus, okay, you know what? Fine. What actually happens is the electrons will move. And so I'll start my positives, but the way my electrons will be, they'll be like this. Remember how I said the electrons can't move within the insulator, but within the atom, within this one atom, the electrons can all move to one side of the atom. That's possible. It's just they can't move within the insulator. Right? So like the electron can't move from here to here. Okay? And so what happens is because all the electrons are like pushing this way, there is going to be a force this way, even with an insulator. Alright? And this is called whatever is up here. Polarization. This is polarization. Polarization. Okay? Now the way it works in a conductor is if I have the same thing, is let's say I have, doesn't matter, this is insulator or conductor. I'm just using this as a charging point, like a wire, let's say. And I bring it near a conductor. Right? Remember how we said protons don't really move? So they'll stay like this. But in this case, what will actually happen is all the electrons will come here. Right? And so as you can see, if you look at the left half, it's negative. And you can see the right half is positive. And so this is also polarization. And there's also a force this way. Alright? Now obviously this also works the other way. So if I had a negative, what will happen is protons still won't move. Right? Protons still won't move. But what will happen is all the negatives will be repelled on this side. So the force will be this way. This is still polarization. Right? Obviously the negatives will also be here because it attracts the thing. But I mean if I put one conductor here and one conductor here, right? So and if they both have the same charge, right, they're kind of both gonna stay neutral and they're both gonna stay like this. Because if they're the same charge, because it will just cancel out. Like if all the negatives come here and all the negatives come here, then they repel, so they go back and they go back. But then all the charges still go through. So these will try to, so just everything cancels out and it stays the same. Alright? Alright, now that we've used these basics, when we solve more problems, you'll kind of get the comprehension for this even better. So if you don't really get it that well, that's okay, don't stress it out. Right? So now moving on to Coulomb's law. Coulombs, this old ass guy who's been dead for a while now. Coulombs, if I can just write his name. Law. Alright. Now what Coulomb's law state is this is this guy's equation, is that the force equals, okay, U1 U2 all over R squared. I'm pretty sure this is a given equation. Now what does it say? Right? It says when you have a proton and you have an electron, there's a force, right? There's a force of this going this way. and then it's going that way. This is force. Let's name this A, and let's name this B. This is force A on on B, and this is force B on A. All right. So remember, to calculate this force is dependent on distance, which is R, and charge. Right? Now we're gonna name this charge, let's say Q1, and we name this charge Q2. So if I only want to find one force, this not both, just this one force, what I'll say is F equals my K, which is a constant. K equals 8.99 times 10 to the 9, and it's a constant. All right, so all you'll need is your Q1 and Q2. So for these problems, usually your Q1 and Q2 is obviously your charge of either your electron or your proton or your electron, which is they're the same for both. Times 10 to the negative 19, I think, coulombs, or something like that. Oops. Right? And so divide it all by your R squared. And that's how you find one force. Now you could do it on the other one, but since there's only two of them, these two forces are the same. Right? So force A on B equals force B on A. And you see here, since the charge is positive and negative, but also the charge for both of them is the same, that means the positive and negative only indicate direction. And so if we have a negative and a negative, direction is that way. And obviously if we have a positive and a negative, we have this way. That's the only thing the negative and positive indicate when it comes to Coulomb's law. Okay. Now the second thing we're gonna go into is superposition. Okay. And what is superposition? Superposition. What this indicates is if I have a positive and negative, let's say another positive here, and I want to calculate the force here. The force on this guy. Alright? Now remember how I said photons don't really like to move because they're so heavy? Like imagine Earth and the sun. The sun affects us, and we technically affect the sun. But because the sun is so much bigger, we don't really calculate that. We just ignore it. We're just like, well, what does it do to the Earth? Because that's way more significant. So same thing here. The electron technically does move the proton a little bit, but it's mostly the proton moving the electron. So if I want to calculate the force, if I want to make this simple actually, I want to calculate the force. Let's say I have one here. I have one here. And I have one negative here. I want to calculate the force. First, I know the effect of these is this way, right? This is F. Let's give this 1, 2, and this is 3. So this is effect 1 on 3, and this one, see, this is how it looks like, right? But we're just looking for the electrons, so we're not gonna put these there. This one is force 1. Force 2 on 3. Okay. So what superposition says is that if there's multiple aspects affecting this one thing, then how about this? Take the effect of each one and just add them together. And so the product, let's say the F net goes this way. And so your F net, the actual effect, equals your F2 on 3 and F1 on 3. That's what it says. So it's F all group on 3 plus F1 on 3 equals your F net. Okay. And obviously you see for this one, if you have a force going this way, you'll have to break it up into your X and your Y and able to in order for you to use them. So keep that in mind. Now doing questions for this unit, charging Coulombs law. And the first question is a plastic rod. So a plastic is an insulator. Let me make this a little thicker actually. Alright. And this is our little insulator because it's plastic. Insulator. Right? And what it says is that a plastic rod that has been charged to -15. So -15 means it's overly negatively charged. There's a lot of extra negatives, more negatives than positive, and it's -15 nanocoulombs. Right? And it touches a metal sphere. There you go. And afterwards, the rod's charge is -10. And so after this, after it touches, what happens is it becomes -10 nanocoulombs. And so what happens is, so what is the question? What kind of charge particle was transferred? So what kind of charge particle was transferred between the rod and the sphere, and in which direction? So from what to what? Okay, so what we know is obviously when it comes to a rod, actually I'll just read the whole rod. When it comes to a rod that is an insulator, and you charge it with some charge, the charge actually stays on the outside. Right, we spoke about this earlier. That's what it actually looks like. And so when you touch it, the charge will move from the insulator to the metal ball. Why? Because the charge wants to be as far apart as it can. Because there's negatives beside each other, and we remember I said negative and negative, they repel. So when you touch it, the charge will want to move into this new space so that it's less compact, right? And so the charge moves from here to here, and obviously the electrons, because there's more electrons. And also the second reason why the protons doesn't move is because the protons are inside, right? We're negatively charged, so the positive ones are inside. And remember how we said, well, in an insulator, nothing really moves, not the electrons, not the protons, and so these will not transfer. But whatever excess charge on the outside will transfer. All right. And now even if we look at the answer, electrons transfer to the sphere. Okay. And so that is our number 1 question. I can get a proper square. No? Okay, I guess not. No proper square. What the fuck is going on? Hello? There you go. Alright, that's question number 1. How many charged particles were transferred? How can you calculate this? Well, we have obviously 15 before, and then we got 10. So 5 went somewhere. Obviously, here they did how many charged particles were transferred, and they did 3.1 times 10 to the 9. So I'm pretty sure here they converted it to coulombs. And so if we take these and we convert them to coulombs, okay, so converting nano to -9, so we have 15 nano, so we have 15 times 10 to the -9 coulombs. If I zoom in, I think it'll be a little bit better. And I have, so this is negative. Negative just says the charge, so it's just negative electrons, okay? Technically, I don't even need this negative. I have this much charge of negative electrons, and then after it became 10 times 10 to the -9 coulombs. That's what it became. Now this is charge. What they're asking for is how many charged particles, right? Each particle is 1 electron, right? And each electron has a charge of 1.602 times 10 to the -19, right? Now we know the difference is 5 coulombs, right? That's how many transferred charge. how much what do you call it? How much charge transfer, how much energy, let's say. All right. And so since we want how many electrons, we'll take whatever many charge and divide it by this many electrons, which is we have 1.602 electrons times 10 to the 9. This will give you how many electrons moved. This will tell you how much charge moved. Each electron is this much charge, and so dividing it will should give you the same answer of 3.10 times 10 to the negative 10 actually. Oops. There you go. All right, so this is 19. And obviously, as you can see, if you look at the math here, 9 and 19, you get a 10. That's how you'd know. All right. So let's do this. Two 1 kilogram masses are some distance apart, center to center, on a frictionless table. So frictionless table. That's our little table, and we have our first mass, and we have our second mass. All right. And the distance apart, so it says 1 kilogram. So let's put 1 kg. This is also 1 kg. And so what this says is are 1 meter apart from center to center. So from center to center is 1 meter. All right. And on a frictionless table, each has a plus 10 millicoulombs, I think this is. So each have a plus 10 millicoulombs. It doesn't say if it's an insulator or a conductor, but I don't think it matters for this question. What is the question though? What is the magnitude of electric force on one of the masses? And since we have their mass, we have their charge, what can we do? So it's not asking, it's asking masses. Okay. So the equation that we used earlier is F net equals F, let's call this A, and let's call this B. We know it's FA on B, and FB on A. This and is the equivalent of a plus. Right? And so since we know the charges are the same, they're both positive, that means they repel. Alright, so the force is actually this way. And we determine that using what charge it is. If it's negative, positive, positive, negative, positive, positive, right? And so this force is B exerting on A. And this is the opposite, right? Of A exerting on B. And so to calculate this, all we gotta do is use our force equation, which is, let's calculate the first force, which is B on A. B on A equals, we have the constant K, okay, which is 8.99 times 10 to the 9. All right. Times the absolute, remember how I said the charge just tells you the direction, so you don't really need to include it here. Times Q1, let's say this is Q1, and this is Q2, okay, times Q1 times Q2. This is a given equation, all divided by R squared, and the R squared is from the center of the object. This is your R, not from here, okay? And so plugging them in, what you'll get is 8.99 times 10 to the 9. And the charge, we have 10 millicoulombs. Now, coulombs, since if you keep both of these in coulombs, you don't have to do the conversion. But the thing is, this one, I think, might mess up with your calculation. So what I would advise everybody to do, always keep it in coulombs, like in one measurement. And so usually that would be coulombs. This is, I believe, 10 times 10 to the negative 3. I'm not too sure about the negative 3. Do confirm that if you do end up doing this for the conversion. And so all this is divided by R squared, and R squared is just 1 squared, and so this actual thing goes away. You multiply your whole thing, you'll get the force. Right? Now, the second, part B. Okay, so part B will say No, I'm kind of confused because there's so much writing. I'm gonna cross this out because we already did it. Yeah, so you should get 0.90. What is the initial acceleration of this mass if it is released and allowed to move? Sorry. Okay. So if it was allowed to move, what we know is our force, Newton's law, force equals ma, right? And so since we know the force, assuming this ends up with a 0.90 equals ma, right? Then taking m, which is 1, you get 0.90 equals 1a, which is 0.90 meters per second squared equals a. Right? And what's our answer? 90 and 90. Yep. So this is done. Now, what is the net electric force on charge A? In the figure below, it's supposed to be 0. Okay. Let's move on. Move this aside so we have some space to work with. Okay, we have A, and we have B somewhere here, and I have C somewhere far here. And I have a positive, and a negative here. Their charges is 1 nanocoulombs, negative 1 nanocoulombs, and 4 nanocoulombs. The distances between them is 1 centimeter. And so what do they want from this question? After you draw your diagram, always now you look for what you want. And so what is the net electric force on charge A? So what we're looking for is net electric force. That means F net, right? F net on F net A. That's what we're looking for, right? Now, what forces make up this total force on A? We know that C will exert some force on A in the opposite direction because they're different charges. And we know B is going to cause some inward force on A because it pulls it towards, because it's negative, right? Opposites attract. And so what this is force B on A. And obviously they're in opposite directions, so one have to minus the other. Since you're using one minusing the other in direction, what I always like to do is say negative is you choose a direction, whether it's left or right. So what I'm going to choose my negative to be is left. Okay, so that's my negative. My negative is to the left. And so the force that B exerts on A is to the right, which means it's positive. Now the force C exerts on A is to the left. That means it's negative, right? And so this is C on A. Okay, now you got to come here and get both of them. So F B on A equals A Q1. Well, we'll use A, B, and C. So Q, I don't know which ones they are. I'm just writing the formula. Okay. And so which Q's are there? B on A. And that means this is the force. B on A. Okay, so which two charges do we have? We have charge A and charge B. Charge A and charge B. So down here, you'll do K times 1 times 10 to the negative 9, all times also negative 1. But obviously we're taking the absolute because we've already determined the direction here. So this is, you can just do the same thing, times 1. Like that, all divided by, we have centimeter. You can keep this in centimeter. You don't have to convert this to meters since all the directions are centimeters. And so we can say 1 centimeter, right? And you'll get some number here. Now you do the same exact thing. Do the C. So if C on A equals K times QA times QC all over R squared, which equals K times 1 times 10 to the negative 9 times 4 times 10 to the negative 9 all over You see, my distance now is actually not 1, it's 2. From here to here, this has 2 centimeters, right? And so you'll get some 2 numbers, plug them here, that would be your F net. All right. And so what is the net electric force on charge A? So he got 0. See if you guys also can get 0 here. What is the force F on the... Okay, so first thing, before we even read this, let's draw our diagram. All right, before we draw, let's take this aside. And there you go. All right. Who doesn't love physics, right? This is more on the complicated example. Do you need extra physics knowledge to solve this? No. Do you need more math knowledge to solve this? Yes. Right, so what we have is electron or proton, proton and photon. And they're connected by a distance 1 centimeter. Right? That's how it looks like. They're all 1 centimeter. All these sides equal each other. All right, and the angle here. I don't really like to write numbers. I always keep it in variables, and then I do it last. And so here on the side, I'll just put theta equals 60. Right? Like I list my knowns, and I know distance r. So this is r. R equals 1 centimeters. And it's constant around all of them. My charges, however, I have a couple charges. I'll name this 1, I'll name this 2, and I'll name this 3. Now my Q1 is 1 nanocoulombs. My Q2 and 3, my Q2 comma Q3 equals 2 nanocoulombs. All right. And now what are they asking? Now I can read it. What is the force F on 1 nanocoulomb charge? They're looking for force on this. Below. Give your answer as a magnitude and direction. So they are magnitude and direction, no problem. Okay, so we come back here to our diagram. We split the problem into 2 problems. You will be doing this a lot in physics. You always split your problem into 2 problems or 3 problems, how many problems. Now, the first thing we're going to deal with 2 charges. Now, this will be pushed that way. That's opposites repel, right? So it will be pushed the other way. Now, the second problem here is this one. We'll push it that way, right? Now, what we have is a axis, right? Remember, whenever you have something at an angle, a vector at an angle, you wanna split it into 2 vectors, your x and y's. And so same thing here, we want to split it into x and y. So my x, this will be pushed that way, this will be pushed that way, and my y, this will be pushed up, and this will be pushed up, right? Now, since we know these 2, same charge, right? Same distance, same charge. That means the force in the x, these 2 cancel out, right? This cancels out this, because when I'm pushing something here, and then I push it the other way with the same exact force and direction, they'll just cancel out. So I don't even need to do my x. All I gotta do is my y. So my y is both in the same direction. That means they add up. That means this actually will, since my x is, this is the direction it'll go. Straight up. Okay? And so now when I'm doing this, what I'll have is, let's say force 2 on 1. And we know that would be this one. This force 2 that exerts on 1. And the force 2 on 1 is K, charge 1, charge 2, all over their distance. Okay, and they did give you the angle, but since your y's cancel out, you don't really need this angle. But you'll trying to think of something. Would you? Yeah, because this will technically also change your magnitude, and we'll talk more about that in a bit. And so we actually will need the to use theta. And so my k, q1, q2 are k times q1, and that would give me, what's my q1? 1 times 10 to the negative 9. My q2 is 2 times 10 to the negative 9, all over. Between q1 and q2 is just 1 centimeter. All right, and so whatever this gives you, and then here we have 3 on 1 equals k, 1 times 10 to the negative 9 times 2 times 10 to the negative 9, and you pay attention, you actually will get the same answer. It's the same problem, same numbers, right? And so these will actually equal each other, and that's why the x's cancel out. And so how do you calculate your actual force? So these two forces that we just calculated will push our electron this way and that way. Now, obviously, we said the x's cancel out. So this magnitude, this F2 on 1, is some force in the x and some force in the y combined. So since we know our x's will cancel out, that means we only want to account for our y, right? And so this value doesn't account for the x's canceling out. And so we can't just add this plus this because, they just go straight up and both arrows are in the same direction, so we add them. No, because technically this is what you're adding up, this vector. And these vectors are not the same. However, these vectors are the same. So you want to get this component of the vector. Now, how do you get that? You can do this, so you can use the z. So this angle is the same as this angle, right? And so if I'm looking at it here, let's say I have a dot here and I have a dot here. And this is how it looks like right now. Always try to simplify your problem. So you see, I'm taking half the problem. And what I know is this angle equals this angle. Now I have a vector that goes somewhere that way. Or actually, well, for this one, this vector will actually go somewhere this way. Right? And I'm looking for this. This angle and this angle is actually the same, because since you use the z, you get this angle. And we know from math, these angles are the same. So this is also theta. Right? And so we know that this angle is our theta. This angle is your theta, and we know both angles are the same, so this is also theta. So now, how do we do the example? Split your vectors. So this is what it looks like, right? This is our theta. This is some force number. This is what we want. Let's name this our y. And so by using our sine, we know sine theta equals y over f, or opposite over hypotenuse. Take the f to the other side, you get f sine theta will give you your y. Now, that's what you do. You want to take this. So you want to take this logic, apply it here. Whatever number you get here, you have f2 on 1 sine your theta will give you your f in the y component, f2 on 1 in the y component. Then you'll do the same thing, f3 on 1 sine theta equals the force that 3 exerts on 1 in the y component. And now, since we know that these two forces are all in the same direction, usually you'd also get your x and add them up. But in this scenario, we actually don't have an x since they cancel out. And if you want, you could do the same logic, except instead of sine, use cosine for both and add them up. Well, but they're different directions, so I have to subtract them, and you'll get 0. So the x's cancel out, the y's add up. So you add these y's, and that's your force. Now the direction, like we mentioned, since the x's cancel out and only the y's force it upwards, that means it's straight up. Okay, so that question is done. Upwards. Okay, so you guys just gotta confirm the number. Okay, so that's done. A nucleus. Okay, so let me take this aside. There you go. Question. So, a nucleus of this, an isotope of the element is the non, however you say it, non with mass. So we know the mass is 125. So always write your knowns right away. Why say U? 125 U. What is that a type of measurement? I'm not really familiar with that. Is I don't know why not. So mass equals 125 U is 6 femtometers. 6, so R equals Well, actually, that's diameter. So diameter equals 6 femtometers here. 6 femtometers, and it has 54 protons. It has 54 protons with charge of 54 times. So, how do you find the charge? Since this is protons, we know each proton has a charge of 1.602 times 10 to the negative 19 coulombs, right? So since we have 54 of them, that we know their total charge is 54 times 1.602 times 10 to the negative 19. And this will equal total charge. Total charge of atom. Okay? And so now let's draw the problem. So we have some atom. Assume it's a circle. And this is, I believe it's called XE. Or XE. Okay? And so we know that has some mass. And we also know that its diameter is some distance. And we know it has some charge. What are they asking us? What is the electric force on a proton that is 2 centimeters from the surface of the nucleus? Assuming this is the surface of the nucleus, this is, so distance 2 equals 2 centimeters. And so this distance, so between here, our little proton is 2 centimeters, right? Or D2. Okay. So what's the question? The question is, what is the electric force? So we have this whole thing that has some huge force or some huge charge. This is the total charge, right? And so this has some huge charge. So we're going to call this Q1. This one is a little charge, Q2. Now we know Q2 of a proton is 1.602 times 10 to the negative 19 coulombs, right? And we know our Q1 is whatever you get here, right? What is our problem? Same thing. Force equals, okay, Q1, Q2 over R squared. Now, remember, you're going to be like, oh, what is my R squared? Your R squared is not this, actually. Your R squared is always from center to center. All right, it's always from center to center. And so we know that this whole thing is D1, right? It's this is D1. It's 6 centimeters. So what we want is we want half of it, because this is from here. So it's D2 plus from the center, which is, this is going to be this is going to be your D1 divided by 2, right? That would be your half. And so your R actually equals your D1 over 2 plus your D2. Okay? And so you plug here, you plug charge 1, what you get from here. You plug charge 2, this one. You divide it all by this distance, and you'll get the force. Now, what is our part B? What is the proton's acceleration? And so, obviously, you'll have F equals ma. Whatever force you get from here, you plug here. Now, we know this whole charge is positive, so we know the force is actually this way. Since this is positive and this is also positive, they repel. This goes that way, and this goes that way. That is the force you'll be getting, okay? Now, this force equals ma, and so whatever force you get, you plug it in. Mass of the proton, okay? The mass of a proton, if I can remember, 1.6 times 10 to the negative 31. No, sorry, to the negative 9.7 kg. That's your mass of a proton. It's a given. It's a constant. Search it up if you want. All right, and so that's how you do that problem. All right, let's take it away. Okay, next problem. Hint: treat the spherical nucleus as a point charge. Yeah, so that's for the force, but it's not a point charge. You're supposed to use it from the center. That's why I'm like, huh? But if you guys don't get a similar answer, then I guess use it as a point charge and don't account for the diameter, I guess. So the thing is with a electron, actually, an electron with an atom, the protons are all in the middle. and what do you call it? The electrons flow all around it. And that's why you have a crazy amount of energy in the middle because of that force. And so, anyways, yeah, if you guys don't get the same answer, just use, don't use d divided by 2. So as you can see here, we use d divided by 2. If that's not the case, remove it, just use d2. All right. What is the force on, okay, this question is very common, extremely common. And so let's draw it out. We have a negative, another negative here somewhere. And I have a positive here. We have some distance. To be honest, I don't know why I do this. I have a better way to do this. There you go. So much easier. All right. So this is our diagram. But usually when you draw your diagram, you kind of understand it better. So I would suggest you guys draw it for practice. But I mean, you guys are not going to be using this anyway. So anyways, okay. So we know, remember, split your problem into 2. What are they looking for? What is the force on negative 10 nanocoulomb charge in the figure below? Negative 10. We're looking for the charge on this one, okay? Give your answer as a magnitude and angle measured in clockwise or counterclockwise. Specify which from the x-axis. Okay, no problem. And so what can we do here is that since we're charging here, we know this force is going to exert on this like that, right? Well, actually, let's make it more. There you go. And this force will be charged, but we don't care about the force here, so I'm not going to put it. Now I know this force right here is attractive, so this will actually go towards it. Okay, and so now we got 2 forces. We're gonna name these. We have Q1, Q2, Q3. All right. Now, what is the force? So they're looking at force of Q3. So force net of Q3 equals. We have the force Q1. Well, force 1 on 3. And we have force 2 on 3. Okay, and so we just gotta take these vectors, add them up, and put them in the same direction. And so F2 on 3 plus F1 on 3. Okay, that's our net force. Now we gotta split them each and get each one of them. And so here we'll do, so F2 on 3 equals KQ. Now which Q? Q2, because you know 2 here on 3, so Q3 will divide by the distance R squared. All right, so K constant, my Q. And remember how we said negative determines which direction? So direction, we're gonna say negative in the X equals left or right. So in the X, let's say we'll go left, right? And then negative in the Y equals up or down, we'll go down, right? And you can also do your, you know, positive Y, positive X, so you know where your thing is. All right, so that's another way to do it. So Q2, where's my Q2? There's my Q2, and it's 5 nanocoulombs. So 5 times 10 to the negative 9 times my Q3, which is 10 times 10 to the negative 19, or sorry, 9 coulombs, right? Convert them to coulombs. And my R, my distance, is 1 squared. Okay, everything in centimeters. So far, so good. This force will be straight up. There's no X component to it. So this is actually our Y, straight up. And so this is my F2 on 3 in the Y upwards. Okay? And that's my first force. My second force is a repulsive force, and it's F1 on 3. Now, the way you get it is you do the same thing, which is K times, what's the charge? We have 15 times 10 to the negative 9, and we have 10 times 10 to the negative 9. Now, divide this whole thing by your distance. What's our distance? The distance you use is this distance, by the way. It's always a distance direct between the two. This is the distance we're actually looking for. So as you can see, when I drew that just made a triangle right there real quick. And so what we can say is take this triangle, see this this little triangle here, and so we know this little triangle, and we know their sides. We know this is 1, and this is 3. What is this? And so we use our Pythag, and so hypotenuse equals the square root of my 3 squared plus my 1 squared. Okay, and this will equal the square root of 10. Okay, and so what you do is you take now I got this is r, right? And so this is r squared, and so what we'll put is root 10 squared. Obviously the square root and the square cancel out, so it's over 10. You'll get some force. Now this force is this way. This force, I like to write it, force 1 on 3 is in this direction, equals some number that you're going to get when you plug into the calculator, right? And so that will create the force this way. I want the x and the y component to it, or else I can't add it to this. I can't do this vector plus like a vector going upwards. How do I add these? They're not even in the same direction. And so how do you get this? Obviously you got the force here, 1 on 3. Okay. Now what you want, you could also use the same, you could also get the angle, right? And so if we know this angle, right, which we can get here using sine, tan, or even cosine, you get this angle here. Okay. Now if I have this angle using my z, this angle is the same. All right. Now if this angle is the same, that means this angle is the same. So if you get this, you get this. Now if I have this angle now, what can I do? Separate it into x and y's. And so first, let's get the angle here. So how do I get the angle? We can do tan theta, or we can do sine, whichever you feel comfortable with. We'll go tan since we have them givens. So tan equals your x over your y. This is my x and this is my y, right? And so what this will be is theta equals tan inverse x over y. So you'll get something for your theta. Now that we have this theta, which is the same as this theta, now we can use it here to split this into x and y. And so my x is simply f1 on 3 sine theta equals my x. Sorry, this would be actually, yeah, actually no, that is sine. But I don't know why I named that as x. Well, I named that as x because it's opposite, but it's not necessarily like that. So I'm just gonna name this like my y. But actually, that will mess up a lot of things. It will be confusing. So let's return it back to normal. All right. Now we have consistency at least. Now f1 on 3 of cos theta, that'll give me my x. Okay. But now we got my x and y's, I can finally add them up. And so my y and this y, as we can see, this y actually goes downwards, this y, and this x goes here. My y downwards is negative. So whatever y you get is negative y. Whatever x you get is to the right. And we said negative is to the left. So that's fine. This stays as positive x. And so after you add your two y's together, which is after you do my f net y equals your f2 on 3 and the y minus different directions minus my f1 on 3 in the y, which you get from here, right? Now you get f net y. You do the same for the x. We only have one x, which is this. So what you'll get is you'll get some force in the y, whether it's up or down. Just looking at this, is it up or is it down? I feel like it's down. Let's assume it's down. Whatever you get here, if you get negative, it's down. If you get positive, it's up. Okay, so assuming it's down, what you'll get is your y down, and then we know our x is positive, so it just goes this way. So then you get, this is your actual f net. This is f net y. This is f net x, right? you can use Pythag. You get your f net here, right? Now, what is your angle? You can use your theta, right? But they mentioned here, they mentioned measured clockwise or counterclockwise from the x-axis, right? They want it from the x-axis. And so, assuming, let's say the x-axis is here, the angle we want, let's say, is this one. So we'll say it's some distance down from the x-axis, right? And so once you get your angle here using tan, right, we can use an inverse of opposite, which is f net x over f net y. You get some theta, just minus it from 90, do 90 minus theta. Now I'll give you your theta 2. And so what you'll say is my f net is clockwise is theta 2 clockwise from positive x. Right, so this is my positive x. I'm going clockwise, some angle theta 2. Alright, so for this question, while it might look a little bit complicated, it's pretty simple actually. Where is it? Hello. Alright, and so the question is asking for is the charge on Q1, and it tells you a piece of information that Q2 is in equilibrium. And so I like to work with these a little bit backwards. And so here, just looking at the figure, if this is what equilibrium means, is that the force left on it and the force right equals 0. In other words, is that equilibrium means either there's no force or all the forces on it combined equals 0, so it doesn't move, right? Now, obviously, we know there's a force. Since this is a plus, this either has to attract, like we don't know the sign of this. These either have to push it away or bring it closer. And since this one is some charge as well, if this was positive and this was positive, then there was only a force to the right. But since this is positive and this is, we'll make this negative, assuming we don't have the color, then we have a charge pulling it and a charge pushing it. Now, if both were positive and this was negative, then there will be only a force to the left. And so this is your only option. Makes sense? That puts in equilibrium. Now, since we know Q2 is in equilibrium, that means the F net, right, usually we'll have F net equals force 1 and force 2. Force 2. Now, since we know this is 0 equals force 1 plus force 2, now we know we'll put our x and y, but we don't need our y, so we'll just put our x. We'll put this positive, so the F2 is negative. So rewriting this, you'll get F1 minus F2. Right, now taking F2 to the other side, I'll get F2 equals F1. Okay, now rewriting this, subbing and stuff, we know the force on F1 is the force that Q3 exerts on Q2. Okay, force that Q3, so Q3, Q2, all over r squared, right? The distance between them. And we also know that my F2 equals my K Q1 on Q2, all divided by, you see the distance is doubled now. So 2r squared, all right? And, or you can add them up and use that, like you use this as a new r, up to you. But this is my second equation. So plugging them in, I'll get, why am I plugging them in? Because here I have my force unknown, my Q2 is unknown, right? There's 2 unknowns. And here Q1 is what I want, so this is 3 unknowns. So I'm going to plug them in. I will get K, Q1, Q3 all over 2r squared equals K, Q, where's my, oh, there you go, Q3, Q2 all over r squared. All right, now actually I'm missing something here. This is force 2, which is 1 and 2, not 1 and 3. Mess that up. 1 and 2. Now, isolating for Q1 because that's what we want. I'm going to divide both sides by Q2, so Q2 will cancel out, equaling 1. I'm going to divide by side also by K. These two will also cancel out. What I'll have left is Q1 equals Q3 times my 2R squared all over R squared. Now applying my squared, I'll get Q3 or R squared all over R squared. Now these two R's cancel out. What I'll get is Q1 equals 4Q3. And since we know my Q3 is 5, 4 times 5 is 20. That's, so you get 20, and it's negative 20. That's the direction, right? And that's it for charge and coulombs. This is all the questions that you might get for this unit. So I hope it helps. Thank you guys for watching, and we'll go to the next unit.